Okay, so here we have, coming back to our problem. So we got this comet, and it's called Comet Norm. This is named after the person that actually wrote this problem. He was a teacher here for a long time named Norm. He was a really good professor. Anyway, so let me get this where I can read your comments. So what I left you with figuring out was how do we solve for one of these two? And the answer that I saw, which was now erased, was to use angular momentum conservation. And that will definitely help us. So the first thing we're going to do is to look at angular momentum conservation. We're going to say the angular momentum at point P should be the same as the angular momentum at point A, where angular momentum is just going to be the mass of our object, which I'm going to say this object has a mass that's equal to m, okay, multiplied by the velocity at that point, which is vp, multiplied by the distance to the sun at that point, which is rp. And then you'd also have to multiply by the sine of the angle made between here and here, but it's 90 degrees, so you just get mvr for our angular momentum at point P. And then the same thing, m times va times ra for our angular momentum over here. Now, this is helpful. The masses cancel, and we know vp and we know rp, but we do not know ra and va. So this isn't enough information to allow us to solve for anything, unfortunately. But we will use this. This is half of what we're going to use. Okay, so what else do we know about this system? What else do we know about this system? Can anyone, and I kind of hinted a little bit about how you do this a second ago. Can anyone figure out how to find RA? Did anyone figure that out over the break? How do you find RA if we know what RP is? Yes, energy conservation, Tom. That's exactly right. That's the other thing we're going to use. So what are the rules for energy conservation? I asked you what the rules for angular momentum conservation is, and someone correctly said that angular momentum is conserved when there is no net external torque acting on a system, right? What's the requirement for energy to be conserved? No work done by non-conservative forces, right? If there's no work done by non-conservative forces, then the energy at perigee should also be equal to the energy at apogee. And I'm just going to let you know that there are no non-conservative forces acting in this system, okay? If there were, the orbit would slowly decay over time, and it would eventually make it so that this object would go into the sun, okay? But the energy should also be conserved, okay? Now, the problem is we don't actually know how to define energy in this system yet, right? I mean, this object's going to have some kinetic energy at point P. It's going to have some potential energy at point P. It's going to have some kinetic energy at point A and some potential energy at point A, right? And the kinetic energy at point P would be 1/2 mv squared. But what's this? Are we going to use mgh? Are we going to use just mass of the... Well, what mass are we going to use now? We have to use the mass of the object. Are we going to use the gravity from Earth? And then we're going to multiply by, like, a height? I don't know, RP or something like this? This doesn't work. And the reason why it doesn't work is because the definition of what gravity is, what we've called gravity, like 9.8 meters per second squared, that only applies when you're really close to the surface of the Earth. If you get really far out into space, you know, as far away from the sun as you can possibly be, then that's not going to work anymore. In addition, this gravity, 9.8 meters per second squared, that only applies when you're on Earth's surface, right? And this object, the comet, isn't even orbiting the Earth, right? It's orbiting the sun. So whatever we would write down right here would have to have something to do with the mass of the sun, probably. And we're gonna derive that here in a little bit, but for now, we can't really do it, right? So unfortunately, even though this is true, since we don't know this yet, we will learn it, we can't actually use this equation, unfortunately. Okay, how about T? What's T? Tonbui, what's T? Is T for torque, or? Tension, or? Period. Yes. What about the period? We haven't used this piece of information, right? How could we use it? What could we use that information to find? just to be clear, I erased that. Energy is conserved in this orbit. It's just that we don't know how to write potential energy yet. So we'll get to that. We can find RA. Is that what we can find? Or what do you mean by, do you mean this RA or do you mean something else? This one? Okay. So what does, so I think you're implying we want to use Kepler's third law, right? Kepler's third law says that the period squared is proportional to, so what is it proportional to exactly? So let's go back and look at what we wrote down. It is proportional to the semi-major axis cubed. So we need to draw this on our picture. We need to put the semi-major axis on our picture. So let's call it A. We know that period squared is going to be equal to the semi-major axis cubed, so, or related to it. So where do I draw that here? Well, to draw that, I also need to draw another line in here, which should be right around here. And then A is this distance. This is A, and then the other distance is also A. Like this is also A over here, right? So we could calculate what this quantity is by using this relationship, right? A. But notice that that is not the same thing as RA, but they're related to each other, right? In fact, I'm pretty sure that if we take RP plus RA, what's that equal to? That's 2A, right? Okay, so that means that we can have kind of a strategy here where if we find A, then we can plug it into here and we can find RA, which is what we're trying to do in part A, right? So let's do it. All right, so to actually use this equation, we need to use a ratio. So we're going to use Earth as our ratio, because the Earth is also orbiting the Sun. So we're going to say that the period of comet norm, which we know, squared, divided by the period of the Earth squared, which we also know, should be equal to the semi-major axis for comet norm, which I'm just going to call A, divided by the semi-major axis for the Earth, cubed. So we should be able to solve for A here. We'll get that A is going to be equal to AE times the cube root of Tn over Te. So we basically want, I'm going to write it like this, and you guys tell me if I confuse you too much. Would you all agree that that's what you're going to get? You solve for A, right? 2/3 power, right? Okay. So we just plug everything in. We know the semi-major axis for Earth was defined as 1 AU. And the ratio right here is going to be, we said that the period for comet norm was 100 years. That was one of the pieces of information that was given. So keep this in mind when you're doing these type of problems on your homework, that if they give you a period, the first thing you should think is, oh, I can find the semi-major axis. And that's going to be useful to me at some point. We divide by the period for Earth, which is 1 year. And we raise this to the 2/3 power. And that will give us an answer for A. And the answer is going to be in AUs. So we take 100 to the 2/3 power. I have no idea what that is. We get 21.5, which is a really big number. That means that from this point to this point, it's like 42 AU, 43 AU. So this is 21.5 astronomical units. Okay, if that's A, like we said, we can basically then come back and use that equation to solve for RA, because we know what A is now. So let's scroll down just a little bit. And now we can say that R sub A should be equal to 2A minus RP. And RP we know, so this is going to be 2 times 21.5 AU minus RP, which is 1 AU. So this should be, let's see, 2 times 21 would be 42. This is going to be 43 minus 1 is going to be 42. So 42 AU is what R sub A is equal to. And because we're going to want to find a velocity later, let's go ahead and convert this into meters. So again, 1 AU is equal to 1.5 times 10 to the 11 meters, or 10 to the 8 kilometers. So let me fix this real quick. So if we do a conversion factor, then this is going to be basically just 42 times this number. So 42 times 1.5 times 10 to the 11. And we're going to get 6.3 times 10 to the 12 meters. If we just use that conversion factor. Okay, that's part A. Again, I'm writing it in meters because we're going to want to use the other relationship that Ton referred to from the angular momentum conservation. We got this. And the velocity was given in kilometers per second. So I put this in meters because now we can just directly solve for the velocity at point A. That was the other piece of this. Part B said to find the velocity at point A. So according to this equation, V sub A is going to be equal to Vp multiplied by Rp over Ra. And now I realize that I was being silly. I didn't actually have to convert this because it's a ratio. That's okay, though. Velocity at P was given to be 29 kilometers per second, so we can plug that in here. So 29,000 meters per second multiplied by Rp over Ra. I'm just going to leave them in AU because we might as well. It's going to be a lot less things to write down. So Rp was equal to 1 AU, and Ra was equal to 42 AU. I don't know why I was thinking I needed to convert this. I guess you'd have to convert this if you were going to use energy. That would be the reason why. And I have done this before where we did that, so that makes sense. Okay, so then VA ends up being equal to 29,000 divided by 42. Oops. Which is going to be 690 meters per second. 690.5, I'll just call it 690 meters per second, which is equal to, just to give you a scale of how much smaller that is, that's 0.69 kilometers per second. So it really shows you just how extreme these velocities can be different from each other. 0.7 kilometers per second it's still pretty fast, right? I mean, if you're moving even close to a kilometer per second, you're going quite fast. If you're going at a kilometer per second, you're going at what, like 3,600 kilometers per hour? Did I do that calculation right? It's pretty fast, right? 1 kilometer per second is pretty fast. So, yeah. But consider that 29 kilometers per second is, much, much faster than that, right? 42 times as fast. So it's going significantly faster when it gets close to the sun compared to when it's far away from the sun. Can I explain how Rp plus Ra is equal to 2a? Sure. It's just a look at the picture. So how are these things defined? So this is the sun. The distance to periapsis here is the distance from the sun to where the planet is at this point. That's Rp, right? The distance R sub A is the distance to apoapsis, which is the distance from where the sun is now to this distance over here. So when taken together, Rp plus Ra defines basically the diameter of this orbit. You might call it that. It's not really the diameter. It's actually what we call the major axis of the orbit, whatever. It's easy to say. It's just like a diameter, right? It's how far apart the edges of the ellipse are. So Rp plus Ra is that. And because A represents the semi-major axis, and it's half the distance, then A plus A has to be equal to Rp plus Ra. Can you see it, Miguel? Okay, no problem. Any other questions about this problem? It's a pretty good intro to these orbit type of problems. They will get a little bit trickier as we introduce changes in orbits. That's going to be kind of where we're going with this. We're going to talk about what happens when you, for example, want to take something from a space station that's orbiting the Earth and bring it back down to the planet, or you want to take an object like a rover. Let's say you want to do something we did recently. We recently dropped a rover onto Mars, and we're going to kind of learn some of the orbital mechanics, I think is what they call it, for how you would take an object that you launch from Earth. If you want to launch it off of Earth and you want to get it to go to Mars, we're going to learn how you do that. It's a pretty hard thing to do, as you can imagine. If you want to launch something from Earth and have it actually hit another planet, that takes a lot of planning and foresight, and these days we do a lot of those calculations with computers, obviously. And even the guidance systems in these systems are controlled by computers, but that's where we're going with all of this. We'd like to understand, how do you get from one planet to another planet? How can you travel between the planets, which is something that we're only now at a point in human history where we can actually do it. So I think it's a good time to start to understand how these things work, especially if you happen to be going into aerospace engineering or planning on working in space. the ideas that we'll describe over the next through the end of today's class and over the next class are going to be pretty relevant if that's the kind of thing you want to go into. So that ends the discussion of Kepler's laws, and what we're going to do now is basically just continue through history, because after Kepler came Newton, and Newton basically, what he did was he wanted to explain Kepler's laws. He wanted to figure out, where in the hell did this weird equation come from? Why is it a cubed proportional to t squared and not a to the fourth proportional to t to the seventh? You know, what is it about the cube and the square here that shows up? Why did this happen, right? I don't know if "why" is the right word, but how does it work? What is mechanically going on in orbits that makes it so that this relationship shows up? And why is it that angular momentum is constant? And why do the objects move in ellipses? Basically, that's what Newton wanted to figure out. Okay, and so that's where we're going next. Okay, so there's this most likely kind of apocryphal story that Newton was sitting underneath a tree in England, and an apple dropped on his head, and like a light switch went off, and he figured out what gravity was. Right? That's what we all learn, is that Newton was sitting under a tree, an apple fell on his head, and he discovered gravity. Right? That's what we learn. The reality is that story may or not be true. It doesn't really matter. The point is that Newton didn't discover that type of gravity. He didn't discover the kind of gravity that makes apples fall from trees, right? He didn't discover the kind of gravity that makes it so that if I take this pen and I drop it, it falls. Because anybody figures that stuff out when they're really young. You learn that there's this thing that we call gravity. You may not give it the name gravity when you're a kid, but you understand that when you drop things, they fall to the ground, right? It wasn't even Newton that first measured that gravity was a constant acceleration, right? That was Galileo. Galileo is the person who, by rolling marbles down like inclined planes and timing them with his pulse, he figured out that the acceleration due to gravity is actually a constant near the Earth's surface. That's not what Newton discovered, okay? This is what Newton discovered. So Newton thought about projectiles. We talked about projectiles in this class, right? And he imagined launching a projectile from a cannon situated on the Earth's surface. So here's the Earth. This is the surface of the Earth. Oops. Here's the Earth, and then here's the Earth's surface, okay? And Newton said, suppose that I place a cannon right here, and I aim this cannon horizontally. So I aim it horizontally, meaning that when the cannonball launches, it's going to come out in a straight line like this. So I don't want it to go up, I don't want it to go down, I just want to aim it horizontal to the Earth's surface, right? And what Newton knew, that was pretty well understood at this time, as Galileo had really gone through and worked out a lot of the details, he knew that, objects that are shot out of cannons follow projectile motion, and that they will start off traveling in a straight line, but they very quickly will basically sink to the Earth due to gravity. Now, if you want to change the profile of this trajectory, right, if you want to make it so that the cannonball goes farther, let's say instead of hitting this point on the Earth's surface, maybe you want to blow up someone's castle that's located over here on their surface, what do you need to do to the cannonball if I want to make it go a little bit farther? Well, you just need to make it shoot faster, right? And if I shot the cannonball a little bit faster, it certainly could go along a trajectory and maybe land at some point right there, right? So what Newton did that made it so that we kind of give him credit for discovering gravity is he said, what if I shot it fast enough, right? I shot it just fast enough that it followed the curvature of the Earth, okay? There certainly must be a way that I can shoot this cannon so that when it comes out, it's going so fast that it never actually reaches the surface of the Earth, but instead follows kind of an orbit, right? And falls all the way back to here, and it's going so fast that it hits the cannon right in the back. He said, well, that type of a motion is what we commonly refer to as an orbit, right? And we know, for example, that the Earth is right here, and the moon is somewhere around the Earth, and we've already figured out that the moon obeys Kepler's laws and goes in... I could at least try to draw a circle, right? Goes in a circular orbit around the Earth. Something like this, right? That the moon travels on a circular path as it orbits the Earth. We saw just a second ago that if we look at modern astronomical data, we know that this isn't a perfect circle, it's actually an ellipse, but it's an orbit, and that's all that matters. It doesn't matter that it's not a circle. What matters is that this is an orbit as well. And what he thought was, this is interesting. If I can, in my mind, imagine firing a cannon so fast that the cannonball never actually hits the surface of the Earth, and in fact comes back around and hits the cannon in the back, if I can at least imagine that concept, then I can say that these two things must actually be the same. That what's happening with the moon, where the moon is constantly going around in this orbit, this kind of somewhat circular path as it travels around the Earth, then the thing that's making the moon do that must be the same thing that draws the apple to the ground, right? So the thing about the apple and the tree story is that the idea was that Newton's sitting under a tree, an apple falls on his head, and he realizes, oh, that's what the moon's doing. It's like the apple falls and he looks up at the moon, and he says, wait a minute, what's the moon doing? Why is it the moon never leaves the Earth? Well, maybe it's just constantly falling towards the Earth due to the same force that draws the apple to the ground, that is to say, gravity. And he said, maybe there's something, and he called it a central force, not centripetal, but a central force. Maybe there's a force that draws the moon to the Earth that I can call the force of gravity, in the same way that there's a force that pulls on the cannonball, that we know this force exists, that we call the force of gravity, right? And he said, maybe these two forces are the same thing. So that's Newton's gravity. The idea that what's happening in outer space is no different than what's happening on the surface of the planet. And this is utterly groundbreaking in science, to say that what things in the heavens are doing is the same as what's happening on Earth, right? That's groundbreaking, to say that it's nothing new. It's not even a new idea. It's still just what we've always learned about. It's still just gravity. The moon, it's going in an orbit. You think it's going in an orbit, but actually what's happening is it's going so fast that the gravity of Earth just can't make it pull towards it. The Earth's gravity basically wants to draw the moon to the Earth the same way that it wants to draw apples to the Earth, but the moon's just going too fast, basically. It's just going too fast, right? And the cool thing about this is, if you start to take this idea to its logical extreme, you can produce any type of orbit you want off of just this same idea. So, one possibility for Newton was, you fire the cannonball and it goes around in this like perfect circular orbit. But what if you fire it faster? Well, if you fire it faster, what's going to happen is you're going to get an elliptical orbit. Because now if you fire it even faster than you did before, maybe your object flies off like this, goes into like an elliptical orbit. I know that's not elliptical, there's only so much screen that I have, and then comes back here, right? And if you fired it at a slightly slower speed, you may be able to get an elliptical orbit that looks something like this. That looks something like this, right? So he realized that it's really just different velocities. It's exactly the same as the concept of a satellite. Exactly, it's 100% the same thing. The moon is basically just a natural satellite, and we of course can put all kinds of things into orbit. So you immediately can see, hopefully, Newton definitely could. I don't know if you immediately are seeing it yourselves, but that you can produce not only circular orbits out of this, but by altering the velocity at which you launch something, you can also produce elliptical orbits. And you can imagine how, depending on the state of the solar system, that's going to determine what kind of orbits the planets are moving in, right? So that's Newton's gravity. There must be some force between the moon and the Earth, and that force must be the same thing that we call gravity. It's not a new force. The most mysterious force in the universe to this day is gravity. The least understood force in the universe is gravity. But this was the biggest, step out of the dark ages, so to speak, that Newton was realizing. It's like, that stuff you see in the sky, those things that you see that are stars and planets and all that stuff, not only, they're subject to exactly the same forces as things on Earth, right? So immediately you start thinking, this is interesting. If I take a rock and drop it near the surface of the Earth, it falls to the surface of the Earth, right? The moon has to be made out of the same stuff, basically, right? Up to this point, I don't know what people thought. Maybe they thought the moon was made of cheese, or they thought it was made of quintessence, or some other type of thing. Stars are made of something different than whatever the Earth is made out of, right? Now, since they're subject to the same forces, it becomes logical to say, well, maybe the moon's just another rock. Maybe it's just a big rock in space. And when you start to say stuff like that, you're really stepping away from the Dark Ages, where science could be kind of mixed with philosophy and even magic. This is during a time, Newton himself was an alchemist. I don't know if you know what an alchemist is, but alchemists were people that were trying to basically turn ordinary metals into gold. And you can't actually do that with the technology they had at the time. And it very much was like magic, okay? And people that practiced alchemy were really just kind of like hustlers that were trying to hoodwink people. They were trying to, they go work for kings, and they'd pretend that they could do something, and they'd create some fantastical operation that made it seem as though they were doing something magical, but it wasn't really magic, right? But what Newton was able to do was to take something that had seemed magical, which is this concept of heavenly bodies, and make it terrestrial, bring it down to Earth, right? Be like, the moon, it's just another rock. It's subject to the same forces as rocks on Earth, you know? And this really drives science forward, right? Like this step forward of being able to kind of like effectively step into space and learn something about what those things are doing has a massive impact on science and really drives science forward over the next several years after Newton. Okay, so that's Newton's gravity. And Newton also went as far to describe how this has to work. Now, when Newton was writing down these rules, he tried all kinds of different solutions. He knew that he had to reproduce Kepler's laws, basically. He knew that his force that he was going to describe between the moon and the Earth right here, whatever form that it took, it had to be able to reproduce Kepler's laws, right? Because Kepler's laws are observational facts. They are observational facts about the way that things orbit, okay? So Newton tried a bunch of different possibilities about how to make this work. How do you make this force work so that it produces elliptical orbits? And by trying different things, what he came up with was this. He said, if I have two objects and I call one mass 1 and I call the other one mass 2, okay? And these two objects could be ordinary objects, like it could be two pins that are separated by some distance, or it could be very large objects like the sun and the Earth or the Earth and the moon. If I take two objects and I separate them by some distance and they have mass to them, the force law that will properly get this to work is to say that there is a force that attracts these two objects to each other, and it goes directly between their centers like this. I'll make it blue. There's going to be a force on that one, and there's going to be a force on the other one as well, because Newton's third law. They're going to be equal and opposite to each other. They form a Newton's third law pair. So this is the direction, this is the force. I'm going to call this the force of 2 on 1. I'm going to call this the force of 1 on 2. So like that. Those forces are going to be equal to each other. The last piece that we need is the distance between the objects. And then what we know is that the force of 2 on 1 is equal to the force of 1 on 2, and it's equal to a constant that we call g, multiplied by mass 1, multiplied by mass 2, and divided by the distance between them squared. We call this an inverse square law. And as you're studying physics and different types of science, you're going to see this show up more and more. An inverse square law is something that happens very commonly in three-dimensional space, which we live in. So this is what we call the force of gravity. And we can state it in a kind of conceptual way in the following sense. If I take any object in the universe, and I take another object in the universe, and I know the distance between them, there is going to be an attractive force that draws them closer together, that tends to want to cause them to come together. And the size of that force is going to depend on how big the masses are. So the bigger the masses, the bigger the force. And the distance away from each other. So if things are really far apart from each other, this force might be kind of weak, unless the masses are really big. And that's basically it. The other piece of it is the gravitational constant g. This is often referred to as the universal gravitational constant. We use the symbol capital G for this. It's approximately equal to 6.67 times 10 to the negative 11. And then it has some units to make it so that when you do gravitational calculations, you get the right units, basically. Okay? Because you want to get newtons, right? Force is measured in newtons. And mass is measured in kilograms. So you have mass times mass, that's kilograms squared. And then meters squared in the denominator. So without a constant right here, the force unit would be kilogram divided by meter squared. So you need to multiply by a unit that has newton meter squared over kilogram squared. That guarantees that you measure the force in newtons. You need to have a constant because this is not how we defined force to begin with, right? We defined force like this. Force is equal to mass times acceleration, which means that 1 newton corresponds to a kilogram multiplied by a meter per second squared. This is just quite simply how we have defined force in the past, okay? Or mass times gravity, if you want to. Weight is mass times 9.8, and the units of that look like this, right? So if you ignore this g right here, if we just take the g out, well, this is not going to give you force now. Can everyone see that? Mass times mass divided by meter times meter is kilogram per meter squared, and that's just not how we define force, right? We could have. this could have been how we defined force, and then we could have thrown a g up here into this equation. But because this equation is kind of seen as like coming before this one, we put our gravitational constant on here. All right? And that's the force of gravity. It falls off as the inverse square of the distance between the objects. That's why we call it an inverse square law. And it's proportional to the masses of the objects. Now, Newton didn't actually know this quantity right here. So Newton predicted the value of this quantity. He got it pretty close. He had to make some assumptions. He assumed the Earth was made entirely of rock and water, and he took the average density of rock and water and used that to eventually figure out what this number is. But it was a later scientist named Cavendish that actually produced an experiment to measure this quantity right here. And it's discussed in your book, but this was discovered by a scientist named Cavendish, and the type of apparatus that he used is still called a Cavendish balance. We have one of these at the school. It's used to determine the universal gravitational constant. Because this quantity is so extremely small, the balance itself has to be really, really precise to actually be able to measure it, but Cavendish was able to do so. And what we'll find out here in a second, after we do a few more things, is that Cavendish, after knowing this quantity, was able to immediately calculate the mass of the Earth, which is a pretty powerful thing to be able to do. There is no way to measure the mass of the Earth using a scale, right? There's no scales that are big enough that we could just take our planet and put them on, as if we could move planets. We can't even do that, right? But by using Newton's law of gravitation, because mass shows up right here, you can figure out what the mass of the Earth is. And to show you how that's done, which is pretty simple, let's just look at a simple example of where we could apply this idea right here, okay, right? So here's the Earth. Wait, I need a bigger thing for the Earth. So here's the Earth, right? And I'm a person standing on the Earth. And I'd like to be able to calculate what my weight is sitting on the Earth, right? So let's use Newton's law of gravity to figure this out. Let's say that this person has a mass of 100 kilograms. It's a pretty big mass, but whatever. A mass of 100 kilograms, right? And let's calculate the mass of the Earth. So this is going to be our goal here. What is the mass of the Earth? All right, we're going to do the same calculation that Cavendish could have done. So what do we need to know? Well, we need to know the distance between this person and the Earth. That's going to be r. We're going to say that r is going to be equal to the radius of the Earth. And the radius of the Earth, which you can look up on a table, is about 6,400 kilometers, or about 6.4. Let's get a little more accurate than that. It's like 6.38, I believe, times 10 to the 6th meters. We're going to want to be really accurate for this calculation. We don't have to be that accurate, actually. That being said, I want to look this up and make sure that I'm not wrong about this number. Equatorial radius, 6.38, yeah. Okay. All right, so our goal is to find the mass of the Earth. We know the distance between these two things. We have a mass here, a radius here, and then we have our force law right here, right? So our force law says F sub g is equal to g times m times the mass of the Earth divided by r squared. But we also know that the force of gravity on this person is the same thing as the person's weight, right? It has to be. I mean, that's at least what Newton's claiming, is that this is the same thing as the weight of the person, right? So, we know how to calculate weight, right? Weight is just equal to the mass of the person multiplied by gravity, right? Where gravity in this case is going to be 9.8 meters per second squared. So if I cancel out the masses of the person here, oh, that's interesting. Look, we've now just proved that the gravitational acceleration near the surface of our planet is actually equal to this quantity right here, g times the mass of the Earth divided by the radius squared. So we basically just proved, just by writing down Newton's law of gravitation, combining it with our definition of weight, we just proved that gravity is constant. this was proved first by Galileo experimentally, but Newton is basically saying this is verified. Like, the gravitational acceleration of a planet depends on g, which is a constant, the mass of the planet, and the radius of the planet. That's what determines the size of g. The bigger that the mass of the planet is, the bigger g is going to be. The smaller the radius, the bigger g is going to be, right? Okay, now our goal was to find the mass of the Earth, so inverse solving this, we get that the mass of the Earth should be equal to r squared times g divided by g. I think I have enough room here. So this is equal to, we take the radius of the planet, we multiply by g, which is 9.8, and we divide by big G, which is 6.67 times 10 to the minus 11. By the way, in case you're curious, as I said earlier, if you're wondering about how we know this, this has been known for a very, very long time. Like, ancient Egyptians were able to calculate the radius of the Earth by looking at how shadows of poles they stuck in the ground changed as they moved between different points. So we get this. What do you get if you calculate this? You should get approximately something like something times 10 to the 24. Oh, I left something out. The radius is squared. This should be squared right here. Sorry about that. So what I got was 5.98 times 10 to the 24. Do you all agree? Why is Control Z not working right now? I don't understand. Control Z. There it goes. All right. 24. And then the unit is kg, kilograms. And we can just check real quick. And that's the right, I know that's the right answer, but somewhere along here you're going to have a mass. There it is. Pretty close, 5.97 times 10 to the 24. Pretty close. Or about 3 millionth the mass of the sun. So it's really powerful. Just by knowing this quantity, and this was, again, this quantity was very difficult to measure. It was measured by a scientist named Cavendish. And knowing this force law, we can measure the mass of the Earth. That's really powerful. It's really powerful. And actually, we can use this number, now that we have it, to measure the mass of all kinds of other stuff, like the mass of the sun, which we can then use to measure the mass of all the planets. This is a really powerful idea. All of a sudden, out of nowhere, Newton went from the conceptual understanding that the way that an apple falls is the same as the way that the moon falls, to all of a sudden having a formula that can allow you to solve for the mass of objects in space. That is extremely powerful. There's the idea that you can find the mass of some object that you have no hope of ever touching. There's no way you can put it on a scale. The only way you can find its mass is through some type of a relationship, and Newton was able to figure it out. Now, this problem of solving for the central force law, for what the law is, was a very difficult problem, and you all probably know at this point that Newton is known for inventing calculus, right? What you may not know is that the reason why he invented calculus was to solve this problem. Basically, the mathematics that he needed to solve again, what was he doing? He was trying to prove Kepler's laws were true by using a central force, and in order to make it work, he needed to invent new mathematics that hadn't been used before. Kind of. I mean, the mathematics he was using were building off of other mathematical ideas, but he basically had to invent calculus to solve this problem because it was that hard of a problem. But after getting through all those ideas, he was able to measure the mass of objects and also be able to describe the orbits of planets, not through Kepler's laws, but now through a force law. When combined with his three, you also need Newton's laws. You still need F equals ma. You need the law of inertia, and you need the action-reaction law. But But all those things together with the universal gravitational equation basically can solve for all. You can predict the motion of the planets at that point. All right, any questions? We don't have much time left, so we'll continue with this next time, but we do have time to do probably one problem. This problem from your textbook. Okay. So when you have more than one gravitational force acting on an object, you basically just vector sum all the gravitational forces, okay? So here's the problem. Many stars belong to systems of two or more stars held together by their mutual gravitational attraction. Figure 13.5 shows a 3-star system at an instant when the stars are at the vertices of a 45-degree right triangle. Find the total gravitational force exerted on the small star by the two larger ones. So, we have 3 stars here. They have masses of 1 times 10 to the 30, 8 times 10 to the 30, and 8 times 10 to the 30 kilograms. The mass of the sun is about twice as big as this one, 2 times 10 to the 30. So these are normal solar sizes. Solar masses are gigantic, just like the mass of the Earth is gigantic, 10 to the 24 kilograms. It's so many kilograms, I can't even possibly imagine how many kilograms that is. Same thing with stars. Stars have to be extremely massive to hold together their gravitational systems. So, we're just trying to calculate the force on the smaller star, find the total gravitational force on this one by the other two. Okay? That's what we're trying to do. Now, some of the work here has been done. I'll try to talk through the picture right here. So we have the distance between the small star here and the big star here is 2 times 10 to the 12 meters. The distance between the two bigger stars is also 2 times 10 to the 12 meters. And the distance between the little star and this big star is like the hypotenuse of this triangle. And our goal is to basically find the force on the little star. Now, the gravitational force is attractive, which means that the force on the little star from the big star up here is going to point in the direction F1. And the force on the little star, due to the star right here, is going to point to the right, F2. And the first question that I would ask is, which of these two forces is going to be bigger and why? Is the force of the upper star or the lower star going to be bigger, and why? We're only looking at the forces on this little star. We don't care about the force between these two guys in this problem, although there is a force there. Which of these two stars would place a bigger force on the smaller object here? The lower is bigger, and what's the reason why? That's right. Smaller radius, exactly. The distance between these two is smaller. It's 2 times 10 to the 12. The distance along this hypotenuse here is definitely going to be longer. So, R is smaller, so the bottom force is bigger, and that's indicated by these two vectors here. F1 goes up and to the right, F2 goes this way, but you can definitely tell that F2 is bigger than F1. Alright, so yeah, we just want to find the total gravitational force exerted, and let's get to it. So the first thing to do with problems like this is just to solve for the individual forces, I think. It's the easiest thing to do. We can say that F sub 1, according to our gravitational force equation up here, should be equal to 6.67 times 10 to the negative 11 Newton meters squared over kg squared. You'll find you're doing a lot of stuff with scientific notation in these type of problems because you're always going to be talking about objects that are really massive. Mass 1, it doesn't matter what we call mass 1 and mass 2. F1 is between this one and this one. So we're going to have our two masses are 1 times 10 to the 30 kg multiplied by 8 times 10 to the 30 kg. And we need to divide by the distance between them squared. So what I would say is if this is 2 times 10 to the 12, then this side is going to be 2 root 2 times 10 to the 12. Because if I have a triangle where the sides are 1 and 1, then the side is going to be square root 2. So 2 times root 2 times 10 to the 12 is going to be what we put down here. So 2 root 2 times 10 to the 12 meters squared. That's going to be F1. So I want you to try to put this in your calculator and calculate it. I'm also going to pull it up on the online calculator so I can just say something about the way we do these calculations. So pull this back up to where we can see everything. So that's what we want to calculate right there, right? So I want you all to try to calculate this in your calculator. And I want to show you like kind of a trick for what you can do if you're using like a TI or Casio or anything that has exponential notation or scientific notation. So this is how I would type this equation in. So 6.67. So what we can do is for the times 10 to the negative 11 right here, what we can do is here we can just click this button and it gives us a little E, or I can just type the letter E. If you want to go to this website, EEWeb, you can do this here as well. But on your TI, that button is there as well, right? See if I can find a picture of an 82 to just show you. It's not probably going to show me an image of it. Let's go to here. Any of these calculators have a button. There it is right there. Right there, that button. EE. So if you push second comma, you'll get this EE button, right? And it does the same thing as what this does. So you write 6.67 and then push that button. It's actually going to give you like a lowercase e. And then just type negative 11 like that. The power of doing it like this is that the calculator will think this is a number. Well, it is a number. And you do not need to put parentheses around it. You don't need to write like times 10 to the minus 11 and then put parentheses around both of these. You don't need to do this. You can just write this whole thing as 6.67e minus 11. That's it. And then same thing goes for the other ones. So this is times 1 times 10 to the 30, so that'd be 1e30 times 8e30. And then divide by, and again, you don't need to use parentheses. Well, I guess we'll need parentheses, so we're going to square this. So we'll put the parentheses on here. This is going to be, so I'm going to write it like this. It's going to be the square root of 2, which on this calculator, I have to do something like the square root 2 times 2e negative 12, or 2e12. And then we're going to raise that like that. Whoops, what did I just do? There we go. So I got 6.67 times 10 to the 25, which we're going to write over here. Do you all agree you get the same answer? And the unit should be newtons. Are you saying yes that you got the same answer, Chris? And, okay, and Alicia, you're saying the same thing? Okay, good. Okay, so that is F1. We also want to calculate F2. We're running out of time here rapidly. I'm only going to go 4 more minutes. So this one is going to be exactly the same. You're having trouble putting it in, Paige? I'll stick around and help you with it after, but yeah, the whole point of going through this is I want you to figure that stuff out. Everything will be the same because the masses of this, now we're doing F2, is this bottom force down here. The masses are the same, the distance now is the one thing that's different, so we just get rid of this. Come on, computer, react, there we go. And there we go. So now we've got our equation here. And we can calculate what F2 is. So F2 is going to be equal to, so pretty much all I need to do is take the exact same equation and then get rid of the square root 2, which is going to ultimately be the same thing as multiplying by 2, I believe. So I think our answer is going to be something like, 1.33 times 10 to the 26th. Okay. And then, now what we have to do is we have to vector add these, okay? And I think the best way to do it is this. So we can break up F1. I hate this picture right here. Pretty much what we have is this. We've got F1 going this way, right? And we've got F2, which is going to the right. I'm not going to draw it. But our F1 can be broken up into components, right? So that one component goes this way, and then another component goes straight up, or to the right, whatever this thing wants to do. Okay, so F could be broken up into components like this, And the angle right here would be theta, and we said in the problem that theta was equal to 45 degrees. So this side is going to be F1 times the sine of theta. This is going to be F1 cos theta. And to get the net force, I'm going to say that if we add up all the forces in the y direction, there's only one force in the y direction, which is F1 sine theta. And if we add up all the forces in the x direction, we're going to have the force F2, because that points in the x direction, plus F1 cos theta. And if we plug in the numbers, what we're going to get is, so F1 was 6.67. Oh, we've got this other calculator up, so we can just use it. So if we take that number and we multiply by the sine of theta, which is the sine of 45, so the sine of, make sure we're in degrees, 45 degrees, we're going to get 4.7 times 10 to the, bad time to lose the, there it is, 4.7 times 10 to the 25 for this one. Do the same thing for this one down here. So this one's going to be F2, which was that, plus basically the same thing, because if I put cosine 45 in here, I'm going to get the same answer, right? So that plus that. And this one's going to be 1.81 times 10 to the 26 newtons. So putting both of those together, we get that the net force that's acting on the smaller mass is going to be, so that was the y direction, this is the x direction. So we're going to have, I'm going to say it's like this, 18.1 I hat plus 4.7 j hat, and then I'm going to multiply both of those times 10 to the 25 newtons. I made this one 18 because 18 times 10 to the 25 is the same thing as 1.8 times 10 to the 26th, I think. And that is what you'll get as your answer. Of course, we can find the magnitude by squaring and adding, and we can find the angle theta if we really want to, but I'll leave that to you all to do. Do you get it, Paige? Great. Okay. I'm going to stop the stream now. Next time, what we're going to be doing is finishing up our discussion of gravitation. We're going to be talking more about orbits. We're going to be looking at problems like, well, this one. Oh, and I didn't copy the other ones because we didn't get to them today, right? Let me see. Yeah, I didn't put the other ones on here. So we'll be looking at this problem, and we're going to be looking at orbit problems, and it may take us a little longer than normal. The other thing that I want you to do before next time is for our last lab of the semester, I want you to read, I'll make this bigger, read lesson 2 in the lab manual, and try to solve the practice exercises. And we will go through them just like we did last time with lesson 1 in class on Thursday. Assuming we have time, it may get pushed to next Thursday. So do this for next time, and lesson 2, I believe, is right after lesson 1. I'm just going to verify before we end today, so I'm not telling you to do the wrong thing. Yeah, lesson 2 is right after lesson 1. It's all about propagation of errors from measurements to calculate results. We're going to learn about if you have an error in one result and an error in another result, and you want to add those results, how do the errors add? If you want to multiply them, how do the errors multiply? That kind of stuff. So that is the plan for this week, and I hope you all have a good